Let's continue talking about the techniques of differentiation. In this particular section, we're going to take a look at the chain rule. And chain rule applied to the composite functions. Okay, so let's compare what kind of function you have to use a chain rule and what kind of function you cannot use a chain rule later, right? First of all, let's take a look at the objectives. Find the derivative of a composite function using the chain rule. Find the derivative of a function using the general power rule. Simplify the derivative of a function using algebra. Find the derivative of a trigonometric function using the chain rule. Okay. So chain rule, let's take a look at the chain rule. So chain rule is the main focus for this particular part of the derivative technique. The rule deals with composite functions and adds a surprising versatility to the rules discussed in the previous two sections. So let's take a look at what kind of functions you could differentiate without using the chain rule, and then some functions you have to use the chain rule to differentiate that. So these are the functions without using the chain rule, like y equals x squared plus 1. And if you look at it, if you put a square root on top of the function, then it becomes composite function. Composite function of a second degree polynomial. And then y equals sine x is a simple function, and y equals sine 6x becomes composite function. Is a composite function of sine x. Okay, y equals 3x plus 2 is a simple function. Then when you raise that to the power of 5, and it becomes composite function. Y equals x plus tangent x, that's a simple function. Y equals to x plus tangent x squared. Let me make it a composite function. Basically, the chain rule states that y changes dy over du times as fast as u, and u changes du over dx times as fast as x. Then y changes dy over du times du over dx times as fast as x. So basically what this is saying is dy over dx equals dy over du times du over dx. Okay. Let's take a look at the chain rule and the theorem about the chain rule. If y equals f of u is a differentiable function, so this is always the assumption of u, and u equals g of x is a differentiable function of x, then y equals f of g of x is a differentiable function of x, and dy over dx equals dy over du times du over dx. So basically, the proof of this is very straightforward. So you have dy over dx. So basically, you rewrite it as dy over t, and times du over du. Du over du is 1. So what you can do is, okay, rearrange it, dy over du times du over dx. Okay, that's how you prove this, the chain rule. So equivalently, you can also write it like this. So basically, you treat g of x as inner function. G of x, inner function. Two steps. Differentiate f of g of x. Differentiate f of g of x And second step, u times the derivative of inner function which is g of x. That's, you can also take a chain rule like that. Okay, so inner function is what we have to pay attention to. Okay, so let's take a look at how we set up u, right? The first one, we get y equals 1 over x plus 1. So this is a composite function of 1 over x, right? Starting from 1 over x. So now the denominator, you set denominator equal to u. Now we turn back into a simple function, y equals 1 over u. And second one, y equals sine 2x. So now whatever next to sine x, that's your u. Now after apply the transformation, then y equals to sine of u. The third one, y equals to square root of 3x squared minus x plus 1. So whatever under the square root, that's your u. So it becomes y equals square root of u. The last one, y equals tangent x squared. So this is basically composite function of x squared, right? And u becomes tangent x. Now you have a turn into y equals u squared, which is a second degree polynomial or quadratic equation. Okay. Now let's take a look at the general power rule. One of the most common type of composite functions is y equals u of x. U of x is already a function, and you raise that to the nth power. The rule for differentiating such a function is called general power rule, and a special case of chain rule. Alright, so general power rule, if y equals square bracket of u of x to the nth power, where u is a differentiable function of x, and n is rational number, and dy over dx equals to put the exponents in front, angles in front, and reduce the power n by 1 for the u of x and times du of dx. So another way of writing this is dy over dx equals n times u of x to the n minus 1 power. Then du of dx actually is u prime of x. Okay, because du of dx equals to u prime of x. So this is like the u of x is in a function. So you differentiate the function f u of x to the n using the power rule, and after that you times the derivative of the inner function. Okay, and to put it in a simple form, you just write u to the n, and the derivative of that equals to n times u to the n minus 1 power times u prime multiplied by the derivative of inner function. Okay, so let's take a look at this example. Find the derivative of f of x equals 3x minus 2x squared parentheses to the third power. So obviously this is a composite function of x cubed. So right here we're just gonna assume this is our u. So that means u equals to 3x minus 2x squared. Then the u prime, we can use the power rule. Derivative of x becomes 1, so 3 times 1. Derivative of x squared becomes 2x, so we get 3 minus 4x. Okay, now we're going to use the general power rule, right? So d over dx in u to the n, right? So it becomes n times u n minus 1 and times u prime. Okay, but for our case, our power is in our problem is u to the third, right? Okay, u is 3x minus 2x squared, so it's u to the third. So it's 3 times u, 3 minus 1 times u prime. Now what you can do is replace u with replace u prime, and then you end up with the answer easily. So 3 times 3x minus 2x squared to the second times 3 minus 4x. Okay, so that's going to be our final answer. Okay, so let's just do a quick review on the product rule and the quotient rule. Find the derivative of function f of x equals x squared times sine x. So here we assume this is f, and that's going to be g, right? So f equals to x squared, so f prime, derivative of x squared is 2x, right? And g equals to cosine sine x, and then g prime equals to cosine of x. Alright, so then we just apply the product rule. F prime times g plus f times g prime. After that, we just replace f prime g prime with given expressions. F prime is 2x times g sine x minus plus, always plus, right, for product rule, plus f which is x squared times g prime which is cosine x. You can leave it like that, or what you can do is factor out x, so it becomes 2 times sine x plus x times cosine x. Okay, so that's going to be the final answer. Second, let's take a look at find the derivative of function g of x equals 2x over x squared minus 1. So here this is our f, that's g. So f equals to 2x, f prime is equal to 2. G equals to x squared minus 1, and g prime, x squared, which is derivative of x squared becomes 2x. Derivative of minus 1 becomes 0, so 2x minus 0 is 2x. Alright, now we just apply the quotient rule. So it's going to be f prime g times g minus f g prime over g squared. F prime is 2 times g, which is x squared minus 1, minus 2x times g prime, which is 2x, over g squared, which is x squared minus 1 squared. So we have 2x squared minus 2, distribute it, minus 4x squared over x squared minus 1 to the second. Okay, so subtract it, you get negative 2x squared minus 2 over x squared plus 1 to the second. Okay, so that's gonna be the final answer. All right, so that's a lot of very frequently, right, when you deal with a derivative of composite functions, you always got to learn how to simplify the derivatives. So whatever result we have is called raw derivatives involving products, quotients, composites, and it would take some time to just simplify that. So let's take a look at this example. We get a f of x equals x squared times square root of 1 minus x squared. So first of all, we're going to turn that square root into exponents. Square root becomes to the half, right? So then this is f and this is g. Okay, so f equals to x squared and prime equals to 2x. And g equals to 1 minus x squared to the half g prime equals to. So now this is composite function. First of all, you gotta apply the. Okay, so it's a d dx u to the n, right? So it's gonna be n times u n minus 1 times u prime, right? So it's very important to multiply u prime. So first of all, we do half, put the exponents in front as a coefficient, and go reduce the exponents by 1 times u prime. U prime is gonna be 1 minus x squared prime. Derivative of that, derivative of 1 is 0. Derivative of x squared is negative 2x. So that eventually becomes negative 2x. All right, and that's what you multiply by. Okay, so if you simplify this, half times negative 2x becomes negative x times 1 minus x squared to the negative half. Okay, so now we can apply the product rule. F times g, right? F prime g plus f g prime. Okay, so just plug in all those expressions. F prime is 2x times g is 1 minus x squared to the half plus f is x squared times g prime is half. No, we simplify that, so it should be negative x. Just use the simplified result, which is a lot easier. So negative x times 1 minus x squared to negative half. Okay, so right here we're gonna factor something out, right? So let's factor GCF of x and 1 minus x squared to negative half. Okay, and whatever remains is 2, and this is 1 minus x squared to the first power, right? Minus x squared. Okay, and then you make it a fraction and flip this negative exponents to the denominator, so we get x times 2 minus 2x squared minus x squared, and this thing becomes 1 minus x squared to the half. Okay, so just simplify a little bit more. We get a negative 3x squared minus 2 over. If you want to write it as square root, feel free to do so. 1 minus x squared. And that's gonna be the final answer. Okay, so the this example simplified the derivative of quotient, right? First of all, again, no radicals, so we gotta turn it into exponents. And the one thing, this is f, that's gonna be g, so f is x, f prime, derivative of f becomes 1. G is equal to x squared plus 4 to the 1/3 g prime. Again, this is a composite function, so get up n times u n minus 1 times u prime, right? So put the exponents in front, 1/3 goes in front. We're gonna reduce the power 1/3 by 1. And times u prime. U prime is the derivative of x squared plus 4. Derivative of that, derivative of x squared is 2x. Derivative of 4 becomes 0, so it's just 2x. Okay, that means you're going to multiply by 2x here. Alright, then after that we can find the derivative. So it's basically f over g, right? So it's f prime g minus f g prime divided by g squared. replace f prime g prime with whatever is there, right? So f prime is 1 times g, which is x squared plus 4 to the 1/3 minus, remember it's different from the product rule, it's minus f is x times g prime is 2x over 3 times x squared plus 4 to negative 2/3. Okay. Then over g squared, right? Okay. G squared, which is x squared plus 4 to the 1/3 square. So then we got to do a lot of algebraic simplification here, right? So first of all, first thing becomes x squared plus 4 to the 1/3 minus 2x squared over 3 times x squared plus 4 to negative 2/3 over, and you have an exponent to another exponent, you just multiply these two exponents. So we have x squared plus 4 to the 2/3. Okay. Now it's not done yet, so we gotta get rid of the negative exponents here. So what we can do is multiply both top and bottom by x squared plus 4 to the 2/3. Okay, so after you multiply that, and this term will become the first term, x squared plus 4 to the 1/3 times x squared plus 4 to the 2/3 becomes x squared plus 4 to the 3/3, which is 1. Okay. The second term becomes 2x squared over 3, and these negative exponents and positive exponent cancel each other, so end up with the 0. X squared plus 4 raised to the 0 power, it becomes 1. Very good. So denominator x squared plus 4 to the 4/3. Okay, so then next step, we multiply both top and bottom by 3. Get rid of the denominator, so we get a 3x squared plus 12 minus 2x squared over 3 times x squared plus 4 to the 4/3. Then the 3x squared minus 2x squared is x squared plus 12 over 3 times x squared plus 4. So definitely need to refresh your algebraic skills if you feel like this is challenging for you. Okay. And let's take a look at this one. So this one we're gonna use the general power rule, right? So we assume whatever underneath this parentheses u equals to 3x minus 1 over x squared plus 3. And then what is u prime? U prime, we gotta use the quotient rule. So this is f, that's g. So f equals 3x minus 1. So f prime is gonna be just 3. Okay. And g equals to x squared plus 3. So g prime is 2x plus 0, so it's just 2x. Now we can apply the quotient rule. So f prime times g minus f g prime over g squared. Then we plot everything here into this. So we have f prime, which is 3 times g, which is x squared plus 3, minus f is 3x minus 1 times g prime 2x. And g squared is x squared plus 3 to the second. And I just distribute it. Okay, so 3x squared minus plus 9 minus 6x squared plus 2x over x squared plus 3 to the second. And combine like terms, we have a negative 3x squared plus 2x plus 9 over x squared plus 3 to the second. So here we're going to use the general power rule, so dx equals to u to the second. So it's 2 times u, 2 minus 1 times u prime. So just replace u and u prime with the given expression, and we're done. So 2 times u is 3x minus 1 over x squared plus 3 to the first, but we omit it, right? U prime is negative 3x squared plus 2x plus 9 over x squared plus 3 squared. Okay, so if you simplify this, so it's 3x minus 1 times negative 3x squared plus 2x plus 9, and denominator becomes x squared plus 3 to the third. Okay, so that's the final simple answer. And the very last thing, we're going to take a look at trigonometric function and the chain rule, right? Apply the chain rule to trigonometric function. So derivative of sine u equals to cosine u times u prime. So differentiate sine u becomes cosine u, and then differentiate inner function times inner function u prime. And derivative of cosine u is negative sine u times u prime times the inner function. Derivative of tangent u equals secant u squared times u prime. Okay. And derivative of cotangent u equals negative cosecant u squared times u prime. Derivative of secant u equals to secant u times tangent u times u prime. Derivative of cosecant u equals to negative cosecant u times cotangent u times u prime. Okay. Let's take a look at how we apply this. Alright, so we have y equals to sine 2x. So here we automatically u is equals to 2x. Now u prime equals to derivative of 2x is 2. Now we are gonna apply the this is sine u, right? Equals cosine u times u prime. And replace u and u prime with given, so we get a cosine 2x times 2. So basically just write 2 first, so 2 times cosine 2x. Okay, so that's your final answer. B, y equals cosine x minus 1. So now this is u, right? U equals to x minus 1. And u prime is derivative of x is 1, derivative of 1 is 0, so it's 1. So now we do dx equals to cosine u. Derivative of cosine u is negative sine u times u prime. Just replace u and u prime with the given expression. So sine x minus 1 times 1. So it just becomes negative sine x minus 1. Okay, the very last one. Y equals tangent 3x. So we assume u equals to 3x. Then u prime is 3. So tangent u. Derivative of tangent u is a secant u squared times u prime. I'll just replace u and u prime with a given number or expression. So secant 3x squared times 3. So it becomes 3 times secant 3x squared. Okay, so that's going to be the final answer. And the very last PowerPoint slide is about whatever derivative rules we have covered so far. We have covered general differentiation rules. That's the very first thing we did. And then we covered derivative of algebraic functions, derivative of trigonometric functions, and then chain rule. Okay. I should definitely go over these rules thoroughly and do some homework problems to become better at it. Okay.